Hello everyone and welcome to this tutorial. In this tutorial, we will see an introduction to Fourier Series and its applications to solving problems. But before moving on to Fourier Series, we need to understand what periodic functions are. So let's say we have a function f of x, where f of x is equal to f of x plus t and also equal to f of x plus 2t. What does this tell us? This tells us that at every interval t, f of x repeats itself, which means t here is our period and f of x is said to what? Be a periodic function. So basically, a periodic function is a function f of x that repeats itself at every interval t, where t is called the period. A good example of this is sine x. By now, you should know that sine x equals sine x plus 2 pi and also equals to sine x plus 4 pi. Now, what does this tell us? This tells us that at every interval 2 pi, the value of sine x repeats itself. So our 2 pi here becomes by now you should know that, period. Good. And sine x is a periodic what? Function. So having understood this, let's see what Fourier series does. So Fourier series, now Fourier series takes a periodic function and expresses it in terms of what we call a series of sine and cos components, which means I could have a function like f of x expressed in terms of what? Sine and cos components. Or we could also say that Fourier series takes a periodic function and breaks it down into the fundamental frequencies. But this will be explained in detail as we progress. So according to Euler, if you have a function f of x that is periodic, it can be expressed as a naught plus summation as n goes from 1 to infinity of an cos nx plus bn sine nx. So what do we do here? We take a periodic function and transform it to this. Now the question remains, how do we figure out a naught? How do we figure out an? And how do we figure out bn? But before moving on to that, I would like us to look at a couple of common integrals that we would find useful along the line. Now the first of them is this. Okay, useful integrals. Number one, we have integral of sine nx dx from 0 to 2 pi. Now what would this give us? Let's work it out together. So if we integrate sine nx, we should get what? Minus cos nx all over n, and our range here is 0 to 2 pi. So plugging in the values, we get minus cos n 2 pi all over n minus cos n 0 also all over n. Now cos n 2 pi is 1, so we have minus 1, There should be a minus here, all over n. Then we have plus 1 all over n, giving us what? 0. So that's the first useful integral. Integration of sine nx from 0 to 2 pi gives us 0. Now number 2, integrating cos nx dx from 0 to 2 pi. If we solve it in a similar manner, like we did here, we should get 0. Same thing applies to this. Integrating sine nx cos nx, or let me call this n, dx. This gives us 0 also. And then we have another one, 0 to 2 pi. Now, sine nx sine mx. Please note, this gives us 0. So that's number 4. I think we have about 8 more. Number 4 more. So let me get to a new screen. So that's now number 5. I've given you sine nx, I've given you cos nx, I've given you sine nx cos mx. So let's see this. Yes, we have cos nx cos mx. This gives us 0 also. And number 6, we have integrating from 0 to 2 pi of sine square nx. Now, this does not give us 0. So let's work it out and see what this gives us. So according to trigonometry, sine square x is equal to 1 minus cos 2x all over 2, which means our sine square nx is equal to 1 minus cos 2nx all over 2. So I can come here to write this, 0 to 2 pi of 1 minus cos 2nx all over 2 dx. And let's factor out our 2. So I have 1 over 2 here. So integrating 1 minus cos 2nx, this should give us 1 over 2. Alright guys, let's go. We would have x minus sine 2nx all over 2. Is that correct? All over 2n. So let's plug in the limits, 0 and 2 pi. So this will give us 1 over 2. Now 2 pi minus sine 2n times 2 pi all over 2n minus, we have 0 as our x now, and we have plus because minus will open the bracket, plus sine 2n 0 over 2n. So calculating this, sine 0 is 0, sine 2n 2 pi is also 0. So we are left with 2 pi. So we have 1 over 2 times 2 pi. And well, our 2 cancels this. We have pi as our final answer. So integrating from 0 to 2 pi sine square nx, this gives us pi. So that's number 6. Let's take number 7. Now, in a similar fashion, integrating cos square nx from 0 to 2 pi gives us pi also. Now, you could work this out in your paper, but I'll give you a clue. Cos square x is equal to 1 plus 2, 1 plus cos 2x all over 2. So this will help you out with your calculation. Now, I think that's all for the useful integrals. But I would like us to note these last two things. If you have cos n pi, it is equal to minus 1 raised to power n. Now why? Because for cos pi, cos 2 pi, cos 3 pi, cos 4 pi, and so on and so forth, the value alternates between minus 1 and 1. So generally, we can say that cos n pi equals minus 1 raised to power n. Also, sine n pi is now minus 1 raised to power n. Now, it is simply 0. So, have you guys noted this down? Or let's continue. So now that we've understood what Fourier series is, we know what periodic functions are, and we've seen a couple of useful integrals. Before we still move on to our A naught, AN, and BN that I wrote earlier, let's look at a couple of conditions which are called Drichlet conditions. How is this spelled? I think it's spelled D-I-R Dirichlet conditions. So now what does this tell us? It's very straightforward. It says if you have a function f of x, for a function f of x that is defined in the range minus pi to pi. Now for this function, if the function is single valued, which means the function is not quadratic, and the function is bounded, meaning it has a lower bound and an upper bound. Now if the same function has a finite number of maxima and minima, oh, finite, what is finite? So if this function has a finite, I will finite it again. Clean that. Has a finite number of maxima and minima. That's 3. Now, if the same function has a finite number of discontinuity, has a finite number of discontinuity. Okay. Now that's number 4. And yes, last one. If the function has a period or is periodic outside the range minus pi to pi. Now, as x tends to infinity, x can be broken down. I've written this before, but this is another proof of concept for it. A naught plus summation n equal to 1 up to infinity of an cos nx plus up to infinity of bn sine nx. I don't know if you guys can see this part of the board. Alright, and we are not done. Now, as x tends to infinity, x can be broken down into this. And also, at a point of discontinuity c, f of x is equal to 1 over 2. We have f of c minus 0 plus f of c plus 0, which is basically looking at it from the left and the right. Don't worry, we'll get to this along the line. So now we've seen the conditions for Dirichlet. We've seen what a periodic function is. We've seen the expression that Fourier series takes our periodic function f of x into. So now what is left is how do we get these constants? How do we get a naught? How do we get n? And how do we get bn? Before moving on to how we get there, we should note that a naught is called DC component in electrical engineering, and we have an, bn, which is like having a1, a2, a3, a4 up to infinity, and having bn, b1, b2, b3, b4 also up to infinity. A1b, A1 and B1 are called the fundamental frequency. They're called what? The fundamental frequency. And A2, A3, A4 up to infinity, B2, B3, B4 up to infinity, they are called the harmonics. I'm going to cycle that out. They are called the harmonics, or they are also called components of the fundamental frequency. So I'm just going to wipe that off. So now back to the constants. So how do we get A naught? According to Euler's formula, A naught is equal to 1 over the period, which is always 2 pi in most cases, integral of 0 to 2 pi, which is our period also, and f of x dx. That's all. Our A of n equals 1 over pi, where pi here is half of our period, integral of 0 to 2 pi, f of x cos nx dx. And finally, I believe you can guess what this would be. Bn is equal to 1 over pi, where pi here is also half of our period, 0 to 2 pi of f of x sine nx dx. So please take note of these formulas. Moving forward, we'll be using them for our questions. I'm just going to give some seconds for you guys to copy it down before I proceed. All right, let's go. So let's take an example. F of x equals to x from 0 less than x less than 2 pi. So we've been asked to find the Fourier series of this function. So don't think too much. What we need here is basically our A naught, our AN, and our BN. And then when we are done, we plug it into our final expression. So let's go. How do we get our A naught? Remember, 1 over 2 pi integral from 0 to 2 pi of the function f of x, which is x in this case. So this should give us 1 over 2 pi. Integrating x, we get x squared over 2. And plugging in our values, we have 2 pi all squared over 2 minus 0 squared over 2. So this gives us 1 over 2 pi. We have 4 pi squared over 2, and everything here goes to 0. So we have pi, it should cancel out the square. We have 2, that will cancel out the 4, which in turn will cancel out the 2. So our A naught here is simply pi. So let's move on to our AN. To get AN, remember, is equal to 1 over half of our period, which is pi, 0 to 2 pi, which is our period now, f of x, which is x, cos nx dx. Now the question is, how do we integrate cos nx dx? So remember from elementary introduction, what we call integration by parts. So I'm going to just walk through that quickly before solving this question. So to integrate by parts, if you have two functions u and v, which are both functions of x, and you can now apply substitution method or other methods of integration, we tend to apply what we call integration by parts in this scenario. And how does it work? Yeah, this is it. So it becomes u dv minus integral v du. Now this will make more sense when I solve this question. But just note, what we have to always cater for at the beginning of this is what we pick as v and what we pick as our u. But then we actually find what to pick as our u. Because if you know what to pick as our u, we know what our v is, which is directly the second expression. So there's a popular acronym AILATE, where I is simply integer, L is logarithm, A is arithmetic, um, T is trigonometry, and E is exponential. So we pick our U in this order. So now back to this question. As I will explain more how to solve using integration by parts with this question. Now, how do we integrate this? We have 1 over pi. Now the question is, according to this, what is our u and what is our v? We are having x here, we are having cos nx here. According to this expression, trigonometry comes after arithmetic and even after logarithm. So basically, x is our u, and once x is our u, we pick the next thing as our dv and not v, like I said earlier. So x is our u, and once you have your u, the next expression beside x becomes your dv. So now let's apply integration by parts. So let's go. We would have an is equal to 1 over pi. Our u dv, which is simply x. Oh, give me a minute. So this should be uv and not udv. This should be uv minus integral v du, and this right here should be udv. So now that we've picked our x and we know what our dv is, our v here will be simply integrating cos nx, and that will give us sine nx all over x. I think I'm going to have to rub this off so I have more space. So I hope you guys got that down. So we'll have x sine nx over n minus integral. Remember, it was v du now, and it was v sine nx over n. And what's our u? Our u is x. So what is the u? 1. So we have dot 1 here. So let's continue. This gives us 1 over pi x sine nx all over n minus, now integrating sine nx over n, this should give us minus cos nx over n. Then we have, remember we had one n here, so this is n squared now. So this should give us 1 over pi x sine nx over n plus cos nx over n squared. So we have 1 over pi. Yes, we forgot to even add our limits. So this should be 0 to 2 pi. 1 over pi, so I'm going to need this. Let me erase the board. So now let's plug in our values. So putting 2 pi first, so we have 2 pi sine n 2 pi over n plus cos 2 pi n over h squared, then minus 0 sine n 0 over n, minus again cos n 0 over n squared. And here we have 1 over pi. Sine n 2 pi is 0. So we have 2 pi. Or no, we don't have 2 pi, because if it's 0, everything changes to 0. So that has gone. Because 2 pi n is 1, so we have 1 over n squared. Sine 0 is 0. Cos 0 is 1. So we have minus 1 over n squared. 1 over n squared minus 1 over n squared gives us 0. So our an is equal to 0. Now let's find our bn. Formula for bn again, remember, 1 over pi, where pi is half of the period, integral of 0 to 2 pi, which is the period given to us, of f of x, which is x. Now sine, instead of cos that we had before, it's now sine nx dx. So let's work this out together. And to solve this again, we'll then do what kind of integration? Integration by parts. So I'll write the formula out here again. uv minus integral v du. And this is our order for picking our u. Integer, logarithm, arithmetic. Is that arithmetic? And trigonometry. Finally, we have exponential. So our u here is x, and our dv here is sine nx. So we have 1 over pi. From the following formula here, we have u, which is our x, and we have v. What is our v? Our v is simply the integral of sine nx, which is cos nx over n, or minus cos nx rather. So we have minus cos nx over n. Then this gives us minus integral of our v. What's our v again? Minus cos nx over n times du. And differentiating x gives us 1. So let's go. Let's plug in our limits 0 to 2 pi. So this gives us 1 over pi minus cos nx over n. Then we can bring out our minus here. So this gives us plus. And integrating cos nx over n gives us sine nx all over n squared, which is sine nx over n times the n that is here before. So now let's plug in our limits from 0 to 2 pi. I'm just going to rub the board off. So let's plug in our limits. Let me rub the board off. So we have 1 over pi into minus x cos nx over n plus sine nx over n squared from 0 to 2 pi. So we have 1 over pi. Now minus 2 pi cos 2 pi n all over n plus sine n 2 pi over n squared minus, no, this will be plus, but by the time you expand this, it becomes plus 0 cos n0 over n minus sine n0 over n squared. So I guess I can rub this off. So now we have 1 over pi. Okay, what is sine n0? That's simply sine 0, and this all goes to 0. Sine n2 pi all goes to 0 because sine 2 pi is 0 and sine 4 pi is 0, and so on and so forth. Cos n0 is 1, but we're having 0 here, so this makes the entire statement 0 too. So we are left with minus 2 pi cos 2 pi n over n. So what would this give us? What is cos 2 pi n? It's simply 1, because cos 2 pi is 1, cos 4 pi is 1, cos 6 pi is 1, and so on and so forth. So we have minus 2 pi all over n. Our pi cancels our pi, so we are left with minus 2 over n as our Bn constant. So to wrap it up again, our A naught is equal to what? 2 pi. Our An, that gave us 0, and our Bn, that gave us minus 2 over n. So by the time we put this back in our expression, remember the expression? A naught, no, our A naught was not 2 pi, I think it was pi, remember. So we have A naught n equal to 1 up to infinity of An cos nx plus summation as n goes from 1 to infinity of Bn sine nx. So using this, f of x, or the Fourier series of f of x, which is x for this question, is equal to pi, which is our A naught. Our An is 0, so everything here tends to 0, plus summation of n from 1 up to infinity. What is our Bn? Minus 2 over n. So I could bring that out here. Minus 2. Then we have sine nx all over n. So again, what's our answer? Pi, let me write this again. So we have f of x equals pi minus 2 summation as n goes from 1 to infinity of sine nx over n. So I hope you got that, guys. In the next tutorial, we will solve more questions on subtopics like half range, function in 2 or more subranges, Fourier theorem. So catch you guys in the next tutorial.